Okay, so let's start. Good morning, everyone. So it's welcome to the closing event of the Sushi project. For those of you who don't know me, I'm Vincent Placet. I'm a researcher at the University of Franche-Comté in France. I lead a research group working on bio-based composites, plant fibers, and their composites. And it's really a huge pleasure to greet you on this event and to see so many of you connected to today. So thank you for your interest in the Sushi project and more broadly in bio-based composites in the bioeconomy. I hope that you will really enjoy this meeting. So for this event, we have prepared a series of presentations in which we will share the main outcome of the Sushi project. So let me share my screen in order to let you see the program. So you can see on this slide the program that we proposed to you. So I will start by an overview of the project, and then we will have 5 sessions dedicated to the different topics that we deal with. Bio-based polymers, hemp reinforcements, bio-based composites and their advanced functionalities, demonstrators and prototypes developing, and environmental sustainability. And after this session, we will propose a closer talk by Ms. Ana Ruiz, our project officer at CBE. At the end of each session, we will let time for questions and answers. So please feel free to use the chat to leave your comments or questions in the chat, or to raise your hand on the Zoom application. Before starting the presentation, I would like also to thank all the speakers from the consortium for having accepted to give a talk today, and also the whole consortium, all the partners, for the fantastic work they accomplished during these 4.5 years, and also for their commitment during the Sushi program, and for the incredible efforts to get this point today, and for maintaining also a really dynamic working process all along the project despite the pandemic period. Of course, I would like to say also a huge thank you to BBIGU, without whom none of this would have been possible. And special thanks also. So thank you also, I was saying, to our external experts, so Professor Ignace Verpust and Professor Jörg Mussig, for advising us all along the project. And thank you also to EAR Partner, our partner recently renamed B4C, Bioeconomy for Change, for organizing this event today. So now it's time to start really the scientific presentation. So let me give you an overview of the project. So SUCHY stands for Sustainable, Structural and Multifunctional Biocomposites from Hybrid Natural Fibers and Biopolymers. So it's, as I said, it's a BBIGU project, a duration of 54 months for a total budget of 7.41 million. It groups together 17 partners within 7 European countries, as you can see here, mixing together academic institutions and SMEs and industries. So the main objective of the project was to valorize lignocellulosic feedstock to develop the new bio-based composites with advanced functionalities. So as you can see on this screen, we had 3 main resource axis. The first one dedicated to the plant fiber processing to develop reinforcements for composite applications. So it used the hemp feedstock. The second axis was dedicated to the biopolymer development using wood-based feedstock. And the last one was fully focused on the development of the composite based on these constituents and to the implementation of advanced functionalities. During the project, we had also 2 parallel tasks related to life cycle assessment and education. One of the main objectives of the Sushi project was to contribute to the development of new bio-based value chains So this concept was introduced by the Bio-Based Industry Consortium, BIC, as you can see on this scheme. So the idea is really to convert Europe's untapped biomass and waste into greener everyday products. And for the sushi project, the idea was to convert undervalued hemp and wood feedstocks in engineering products. So you can see the positioning of the partners in this value chain that we developed during the project. And to be more specific, we worked on two different hemp value chains. The first one dedicated to hemp, so from field to processing to the half products in order to obtain a reinforcement for composite application. So as you know, hemp is a really good candidate to expand the purpose-grown biomass. You can see the main assets here summarized on this slide. And the second value chain was mainly focused on wood building blocks extracted from wood byproducts in order to generate building blocks and then polymers fully bio-based. So here you have two examples of building blocks such as isoeugenol and ethyl guaiacols that were used to develop bio-based epoxy thermosets. And we interconnected these two value chains because by definition, a composite is an assembly between a reinforcement and a bio-based polymer. So the idea was really to interconnect these two value chains in order to obtain our final material products, the composite. So you can see here that we valorized some byproducts coming from the wood transformations to develop the polymers. And we extracted the long fibers and the short fibers from the hemp to obtain the reinforcement. And then we were able to valorize this composite. It's also important to consider the other outputs, which were not in the scope of the sushi project, but which are quite important also to obtain an economically viable value chain at the end. So after using and developing this constituent, we obtained some composite materials. So we targeted high strength to weight ratio. We tried to enhance the durability of these materials, their fire retardancy, and also to exploit their vibration damping capacity. And we illustrated it at the scale of 4 demonstrators. So unfortunately, we are not able to showcase it today, but the demonstrators are here in Besançon today, and we can see it within the consortium, but we will try to give you the maximum of details and view during the further presentations. So these demonstrators are a high-end loudspeaker system, a monocoque structure for an electric scooter, some electric aircraft interiors, and some automotive interiors. The project was organized following these 11 work packages. The first one was dedicated to the project management, and the 11th to the dissemination and exploitation. The 9 other work packages were scientific work packages dedicated to the biomass processing, the composite manufacturing and selection, and the advanced functionalities implementations. And we had also a parallel work package, the number 10, dedicated to the sustainability aspects. So during the project, we have recruited some PhD students, and most of them are graduated today or coming soon. So you can see here on this slide their names and the topics of their thesis. And we had also 10 postdoc researchers and 25 master students working on the different tasks proposed in the project. In terms of community and network, so we created a successful and sustainable cooperation between the different partners, academics, industries, and SMEs, and also with external stakeholders. We participated also at the emergence and development of the bio-based composite community in Europe. A good example is the co-organization of the first edition of the European Summer School on Bio-Based Composites, the EES-BBC event. So it was co-organized with 3 other European research projects, Netfeed, FiberNet, and Flower. And for this first edition, held in 2021, it was quite a good success with 150 attendees from 27 countries. And we tried also to develop this community on the social networks, Twitter and LinkedIn. Most of the results that you will see today are going to be published in scientific articles. To date, we have published 32 articles in high reputation journals, owing to different disciplines and different research areas, as you can see here, dealing with biomass fractionation and processing fiber, bio-based material durability dumping, and so on. And we had also 46 communication in conferences, and we have prepared some tools also to enable a wider audience. We will disseminate soon a public book of final results and a video also summarizing the main outcomes of the project. So at the end, we obtained these main impacts in terms of results and outcomes. So new AMP reinforcements, new bio-based composite. We contributed also to a sustainable management and efficient use of some natural resources, such as AMP and wood byproducts. We contributed to decrease the carbon emission and increase the sustainability and competitiveness of the European bio-based composites sector. It includes the Sustainable Development Goals 9, 12, and 13. So that's all on my side for this overview of the project, and I will now leave the floor to our first speaker and first chairman, Joseph Samek. Samek is professor at Stockholm University. So Joseph, I give you the microphone for the next part of this event.
Thank you, Vincent, and good morning, everyone. My name is Joseph Samek, as you heard, and I am going to chair the first session, where I'm also speaker together with Christophe Thomas from Paris. So these are the people that have been involved in this project, and I'm upstream of the process. So we want to extract chemicals from biomass and then convert them into monomers that can be used for producing the glue, the polymers for these composites. So to give you an overview over the current biorefinery, we have the trees that can be divided roughly into 3 parts. One is the timber part, which has the highest value. Then we have the pulp part that also has a high value. And then the third part is the tops and branches. So the timber is cut into logs, and you get about 60% out of this third that goes into high value products. And then 40% goes into small pieces, shavings, and also sawdust that has a lower value. And then of the pulpwood, you get out about 50% as boxes and paper, and then 50% is burnt in the pulp mill. And then the rest, the tops and branches are left usually in the woods, or they're extracted from the woods and burnt up, incinerated. So the current biorefineries has about 1/3 of yield of high value products, and 2/3 end up as waste value or incineration value, which is a low value, unfortunately. So our ambition has been to use this part of the forestry and also the bark that is incinerated to generate these chemicals that can be used in these applications. But we also want to apply sustainable chemistry to convert the wood into monomers that can be used for these applications. So there's the 12 principles of green chemistry. So important aspects is that we don't want to generate any waste. We want to have good mass balances. We want to use benign reagents. We don't want to use toxic reagents and generate toxic chemicals. And of course, we also want to use green solvents. That is usually a big problem in chemistry. So our approach was to use the forest residues and the bark. And in the forest residues, we have both a lot of lignocellulose, that is the wood part, but also bark. And then apply the 12 principles of green chemistry and to convert these now into these monomers to produce polymers. So I will just give you a first example on how we thought in the beginning and how reality came up during this project, where we have learned a lot actually about sustainability. So we wanted to produce this monophenolic compound that can easily be turned into such a compound that can work as a monomer for polymers. The problem is, or the question we can ask is, okay, if we do this, how high are the yields and what is the rest? And we found out the hard way in this project that only 10%, we can only extract 10% to give this compound, and then we have 90% that would then end up as a waste. And of course, this is not sustainable. So we have to find applications for all of these 90%. And this is a big challenge in transforming biomass to valuable chemicals. So to make a long story short, what we did was we chose a few different feedstocks. First we chose birch and pine, but then we also added the hemp hurd, and the hemp hurd is the piece of the hemp that does not go to fiber, and it looks like wood more or less, and also birch bark. And then we systematically evaluated these feedstocks for generating both the monomer, but also in terms of mass balance, we don't generate a lot of waste, as I showed on the previous slide. So that means that we have to evaluate the fractionation, and then also how good the monophenolic compound that we get out, how well that performs as a polymer. And then also, of course, the chemistry to produce this. So this is a little bit a crowded slide, but you can see, for example, birch, the catalytic fractionation, that is the extraction, works pretty well. The synthetic chemistry works pretty well, but the thermoset properties were not good. So this will mean that we would have to use a lot of material to compensate for the poor properties. If we go to the pine instead, it is the reverse. So the catalytic fractionation does not work so well. We get a lot of waste products that we cannot valorize. And the synthetic chemistry works pretty well, and the thermoset properties are also very good. But because of this problem upstream, we cannot get a good life cycle assessment. The sustainability is poor. So that made us turn to birch bark. And here we were able to get a very good catalytic fractionation, so we don't get any wastes. And I will show you how we did this. And the synthetic chemistry also worked nicely. We could apply the 12 principles of green chemistry. And then also the thermoset properties are good, so we don't have to use a lot of material. And because of this, the sustainability was evaluated, as you will hear later on in the presentations, positively. So the birch bark, we could fractionate this. So this is birch bark. It's a big polymer, and we could apply green chemistry to break the chemical bonds, and we could liberate the chemicals. And what we did was we applied recirculation instead of distillation of the solvents. And this was crucial for sustainability. So we could come down below 3:1 solvent to wood ratio before we distilled it. And then the oil that is generated was transferred to a distillation tower, and 1.6% goes to this ethyl glycol that we could then apply green chemistry to produce this diapoxy bis glycol monomer for polymers. And the rest we could hydroprocess to generate biofuels. So in this way, we don't get any chemical waste. Everything goes into high value applications. So to our conclusions, to make a long story short, is that we have developed a value chain from bark to monomer and thermoset and biofuel. And we have evaluated positive green chemistry, and the mechanical properties of the polymers generated from this monomer have been also good. And the sustainability has also been positive. We have also evaluated other feedstocks, but they have been found inferior because of either the chemistry or the mechanical properties. And then, of course, the sustainability is not acceptable. So with this, I leave over the word to Christoph Thomas.
Good morning. Can you hear me? Yeah?
Yes.
Okay.
Yes.
Cannot see me, but I don't know why. So now I will talk to you about our work on building blocks to obtain bio-based polymers for biocomposite applications. So first of all, a quick reminder. A composite, as you all know, is a material which is produced from two or more constituent materials. And these materials are merged to create a new one with different properties. And for instance, for fiber reinforced polymer composite, there are two different types of materials. One is the polymer matrix, the binder, and the other is the reinforcement, the fiber in that case. And the properties of the matrix are improved when the fibers give it their exceptional physical and mechanical properties. And typical examples are listed here and can result in composites that are less expensive, lighter, stronger, or more durable. So the goal of our work in that case was to find new synthetic approaches to fully bio-based polymer materials in order to replace petroleum-based polymers. And this work was carried out in Dijon and in Paris, and was in close collaboration with Stockholm University. And we were interested in two different routes involving the development of new thermoplastics, but also in the development of thermoset epoxies. In the SSUCHY project, we had several specifications to meet. First of all, we wanted to obtain good thermomechanical properties with, for example, a high transition temperature above 100 degrees. Also, the improvement of the flame retardant properties of the synthesized material was particularly targeted. And of course, it was important to increase the content of bio-based carbon in thermoplastics and also in epoxy resins. So epoxy resins are widely used in the preparation of thermosets because they have excellent thermomechanical properties. And among them, GBA resin represent around 70% of the commercially available epoxy resins. And this prepolymer can react with different type of hardeners, such as polyamines or anhydrides. However, GBA is composed of bisphenol A, which is subject to strict regulations because it's an endocrine disruptor. So developing a greener alternative for bisphenol A is a real challenge. So we use the different epoxy prepolymers prepared in Stockholm in curing protocols in the presence of cyclic anhydrides as hardeners. And the most interesting formulations so far have been obtained with isogenol derivatives in combination with camphoric anhydride. But we have also achieved promising results with bisguaiacol phthalic anhydride. Glass transition temperatures above 100 degrees were obtained, as well as Young modulus values above 2 gigapascal. And in the case of the isogenol derivative, a greener formulation called BioHygenox was developed, leading to a significant reduction in the volumes of organic solvent used. Then we prepared mini samples of composite dedicated to bending test and incorporating hemp fibers. In terms of mechanical properties, the bending test showed values comparable to those obtained with GBA resins, demonstrating the possibility of finding alternative bio-based molecules from lignin. Also, starting from an isogenol derivative, we synthesized a new bio-based flame retardant during the project. And this compound can be used as a copolymer in combination with other diepoxy precursors, increasing the rate of residue and improving the flame retardancy of resin samples. For the preparation of thermoplastics, our strategy was first to evaluate the feasibility of the synthesis of new polyesters by a one-pot approach, which avoid the formation of side products and the purification of intermediates. Using this approach, we were able to prepare new thermoplastic polyesters and to obtain a green process to obtain to synthesize camphoric anhydride, which can either be used as a hardener or as a co-monomer. Thus, the two most promising thermoplastics we obtain have been prepared to form mini samples of composite dedicated also for bending test. However, the first experiment performed showed that our polymer were too brittle. So to avoid this problem, we used bio-based plasticizers, but unfortunately, we obtained a polymer on a larger scale, which has a TG that was too low. So in order to obtain a more processable material, we then decided to investigate a similar one-pot sequence starting from methacrylic or acrylic acid. And again, this one-pot approach makes it possible to directly obtain bio-based materials without needing to isolate or purify intermediates. And to form our monomer, we used bio-based alcohols, such as ethyl lactate or vanillin, which is one of the only industrially available aromatic product of lignin. Starting from these monomers, different types of polymers can be obtained, such as homopolymers, random copolymers, or block copolymers. And the alcohols used give plastics their main thermal or mechanical properties, such as flexibility or hardness. And for instance, the homopolymer of ethyl lactate displays a TG at 47 degrees, while the homopolymer of vanillin methacrylate has a much higher glass transition temperature. And in all cases, we were able to obtain copolymers with a very high TG by using vanillin as a comonomer. So we believe that this kind of polymethacrylates could have a great potential. Thank you.
Thank you, Christophe Thomas, for your presentation. We are a little bit behind schedule, but I advise one question. If you please raise your hand, and then otherwise you can, of course, use the chat function and continuously ask questions to the presenters. If there are no questions, I leave the word to Vincent.
Okay, so good morning. So I am Pierre Wine from École Nationale d'Ingénieurs de Tarbes in France. And I'm going to show you some of the results which are obtained in the frame of two work packages. So work package 4 and 5, dealing with mostly with the value chain, the hemp value chain, from the field to the reinforcements. So you can see that many people participated. I hope I didn't forget anybody to contribute to this work. Different approaches were considered to work with the hemp, to produce the hemp, to harvest it, and then to manufacture rovings and reinforcements, roving yarns and reinforcement. First approach is to consider what is happening in the textile flax production zone, which is in blue in the small map from Normandy to Netherlands. In this zone, there are machines, fiber extraction machine, which are available, sketching and hackling machine. And there is also an established value chain for flax. And the idea is to use this value chain with modification to hemp. And the other approach is to use in other places where all those equipments are not present, to use other types of machine, more classical consideration for field in the field, and then for fiber extraction, use breaking and carding routes from randomly aligned durated stems. I'm going to come back to that a little bit later and start with the first approach, the one which uses the textile flax value chain. And the idea, okay, it's a lot of boxes in here, but the idea is to adapt, maybe a little bit simplify the textile production method. So with a lot of steps which are quite similar to the one of the textile flax, but with some few differences, especially for the harvesting with different machines which are required because the plant is not the same. But by using then, except this harvesting machines which are different, by trying to use as much as possible the textile flax machines for the field operation and for the primary processing, as well as the secondary processing, and trying to go directly from the roving to the fabric without using the classical wet spinning approach, for example. So going now to the beginning of this chain to the field, hemp was grown. Hemp was grown in Italy, in the north of Italy, close to Piacenza, and hemp was grown, well grown, and tests were made then for the harvesting. Harvesting, of course, by hand is possible, but harvesting with machine is a challenge, especially when we go to the textile flax value chain. So the idea is to have a machine which can mow the hemp stems, lay them down on the ground so that they can be managed by returning machine for the durating procedures. So basically it has to be returned between once, twice, 3 times, depending of the weather. One of the issues as well, because the stems are most of the time 2 meters high, is to obtain 1 meter long stems because flax machines are made for 1 meter long stems. So in this work, the approach was one approach was to use this machine, which consists in cutting the flax, the hemp stems in two, to give this kind of windrow, and then bale the hemp. After those field management considerations, which are not easy consideration, which is a big challenge, with machines in here which were used, which maybe are not fully perfect, but which work and which can be considered for industries. Some other machines are arriving, and I wanted to tell that maybe they are not part of the subject of sushi, but it is part of the future, and some new prototypes of harvesting machine were developed since we performed the test. And I think it's very important to mention it because in the future, hemp will be really available with industrial harvesting machines, which were, let's say, almost ready in 2021, and which will be ready in 2022. And I can give you an example of what is happening in Normandy, for example, with those harvesting machines which are developed, and you can see that exponential growth of surfaces, of hemp surfaces will take place. So coming back to our results, you can see that some hemp was harvested. And what is important is to look at the stem yield, because growing hemp is possible in many places in Europe. It's been proved for many years, but in what extent the one which was grown in the frame of sushi is suitable for industrial production. And you can see in those results that depending on the variety between, let's say, 8 tons to 11 tons per hectare of stems and of durated stems were harvested. It's a lot. It's very high yield, and the work which was done was obviously very good. So high biomass was obtained. Biomass is good, but what is really our interest are fibers. And for fibers, fibers were extracted using sketching and hackling. So there were tests were performed at the lab scale with different settings. A lot of settings were tried. And we managed to obtain very high yields at the laboratory scale. 27% of the stem mass transformed into fibers, and 18% after hackling. It was very difficult to transfer those settings to the industry, but still some pretty encouraging results were obtained with 12% of long fibers obtained after sketching, and 18% of toes for Futura 75 variety, and a little bit more fibers in the Fiber 79 variety with 14% of long fibers and 23% of toes. At the end of the day, fibers were obtained at the industrial scale at Terre de Lin. I want to mention them because they were not officially part of the project, but they had a crucial role in there. And 500 kilograms of hackle fiber were obtained at the end for further transformation. Further transformation, it means transforming those hackle fiber into slivers and use drawing, doubling and roving to transform those fibers into different types of yarns. So roving type yarn, which are the ones which were mainly used, but other types of yarns like co-wrapped also yarns obtained originally from those rovings and mixed with polyamide thermoplastics. This is the first approach, going from the field to the yarns with the sketching hackling route. Now, what about the second approach in territories where sketching and hackling is not available? So, for example, in places where hemp is also harvested for seeds, or when it's not harvested for seeds, but when it's not possible to harvest it by machine laying down the stems, and when the stems are randomly aligned, like you can see on the picture. In this case, the strategy was to adapt and improve what is normally called the short fiber method, or the tow approach, tow method. So once again, with also field operation, primary and secondary processing. So I try to be a little bit quick in there. We used for this approach breaking rollers and breaking card machines in collaboration with the Impact company, which is in the southwest of France. So this company, they have a device with successive breaking rollers, as you can see on these diagrams, and you can see the machine, the actual machine on the right. So in there, it's possible to introduce randomly aligned stems. Just want to tell that it's important that the stems still need to be rated. And then after breaking, some fibers like this, which are again randomly aligned, can be obtained. There are still a little bit of sheath remaining. And this is why those fibers need to be introduced in a card. So breaking card, which has two main important roles. The first one is to homogenize the fiber length and to try to align the fiber as well. At the end of the day, after the breaking card, some fibers, some big slivers, like here in the part E, can be obtained. And those slivers can be drawn with a machine we saw previously, can be drawn, doubled, homogenized to obtain some slivers like that. And at the end of the day, roving type yarns as well as for the sketching hackling approach. Don't want to give you too many numbers. Of course, at every scale, the fiber were characterized, fiber rovings, yarns were characterized. Just want to show you that at the end of the day, the fiber obtained by the sketch hackle approach and the one obtained by the breaking card approach globally give not exactly similar results, but quite equivalent, globally equivalent. Maybe some of them we have a better stiffness with the sketch hackle fibers, maybe a higher strength with the carded fibers. But both of them are really suitable for the composite reinforcement, and that is really the good news. To summarize this, I can try to show you a short video showing the whole value chain. So this is after sketching. So yeah, at the end of the sketching, and very soon now that's input of the hackling machine. Output of the hackling machines, and then you have this machine transforming the hackle fiber into a sliver. Okay, and now weaving and also braiding, which was carried out. To finish the presentation, of course, I want to indicate that you saw in the video that some fabrics were made, different fabrics were made from the roving type yarns. It was mostly from the sketching hackling route. So tests were performed at the lab first, and then at the industrial scale, as we show in the video. So what was important as well, it was the weavability of those fabrics. So of course, if there are fabrics, they were weavable, but this was tested, and this was tested with the Scotch and hackle rovings. So it was globally okay. And some woven fabrics and some braids were manufactured, as you can see before. And with carded roving, it was more difficult. Maybe some improvements still needs to be made, but they were successfully woven in weft at the lab scale, at industrial scale. Just show you some of the fabrics and braid, woven fabrics and braid which were made with more than 20 patterns of woven and quasi-UD, which are ready and which were transformed into composites from 100% hemp and co-wrapped rovings and the braid as well. And I am at the end of the presentation. So with different papers from different groups which illustrate the work which was performed in this field. So now I think I will ask Clara Dughetti from Linificio company to introduce how the company worked in the project. I don't want to tell too much, but I just want to say that the Linificio company was very, very important for the work which was presented. They had a really, really crucial role. And I think maybe they can give their feeling about what they did during the project.
Stop the sharing.
Thanks, Vincent.
All right.
Can I share my presentation? Okay. Okay, good morning, everyone, and thank you for being here. I'm Clara Dughetti, so I'm an agronomist, and I recently started working with Linificio as innovation and sustainability manager. So today I'm here to present the results that we've achieved with the project Innovative Hemp Chain for Compositive Reinforcement. So presentation of our reality, Linificio Canapificio Nazionale is the European leader in the production of flax and hemp yarns, with an annual production of about 4.5 million of kilograms of yarns and 1 million meters of fabric. Our turnover is about 50 million euros per year, as an average of about 3 years, last 3 years, and the firms involves about 950 employees. The flax industry where Linificio operates in is highly integrated and 100% European. And here, Linificio is the innovation hub for research and development. Furthermore, since last year, we became a benefit corporation. So the industrial results achieved with this project include firstly, we start with a hemp fiber, cultivated, grown, and processed in France and Italy. We got there by studying, developing, and process an innovative process for producing a low twist yarn with the tautness and the strength valuable, suitable for being woven. Second, we advanced the production of natural hemp fiber reinforcement that can be used for composites applications. Currently, we can produce these bidirectional supports as hemp substrates with different characteristics, so such as weight and texture and composites with complex shapes. So we can be very online with the market demands. Now, I am very pleased to show you some pictures of our processing cycle. So first, you can see from the first picture, there is a hemp icing sliver that that arrives in our plant. The second illustrates how it looks before preparation and before processing. So the processing phase serves to obtain a clearly more refined sliver. And the third one, you can see the low twist yarn that we obtained. So the next pictures, the fourth, the fifth, and the last one, show you the detail of the loom processing and the making of natural hemp fabric. And here I can show you the video of the weaving process. So, sorry. So, as far as industrial prospects, we can include, of course, the development of a new market, but how much is worth this new market? Our prediction is that between 2022 and 2025, the market for hemp reinforcement yarn or fabrics for compositive materials could be worth 10% of our yarn production volume and 15% of our production volume of fabrics. So, of course, besides opening up a new market, there is, well, we cannot underestimate the very topical aspects linked to environmental and social sustainability. So we will have an European supply chain, not only for the fabrics, but also for the yarn. And so, because we think that we will be absolutely able to implement this production in Italy, so to our production site. Therefore, there is an impact, of course, for ethical and social aspects. In economic terms, we estimate to invest about 2.5 million euros for machinery production and for equipment, and by bringing new resources to our plant in Italy. So we will increase our social impact again. So thank you so much for your attention. I was very fast, so because we are on time. And of course, thank you on behalf of all the staff of Linificio and Canapificio, and Pierluigi, of course, and of my person. Thank you.
Well, thank you for holding the time. It's nice, and also very happy to learn and find out all the investment and really finally that to show that the project is a success also for the company, because at the end of the day that's the goal of such project, I think. And well, I think we have
So
time
if you
for
have
some
any questions, please ask us, because there is also Giorgio online. So maybe, you know, we can have a discussion about it. Thank you.
Well, yes. So, question, I don't know if anybody has
Quel est le problème, Pierre?
Okay. Yes, there were some few questions on the chat. So I think I answered one of them to Arnaud there. Yes, harvesting was performed at both full flowering and seed maturity for the SSUCHY hackling approach. Globally speaking, so I didn't give any details in the difference between both, but we didn't have many differences and very obvious difference at the composite scale. And for the carded root, the hemp we used was hemp which was harvested after seed harvesting, so it was after seed maturity. And there was another question by Jörg Mussig about IFBT results and why the strength of the carded composites was higher than the one of the sketching or sketch hackled fibers of composites. Really, it was a surprise. We didn't expect this at first. And the results are very new, so I don't know if I have a real good explanation. Maybe one of them is the fact that we use probably a little bit less steps, less machine steps with the carded approach. And we need probably to check if the number of defects is the same in both approaches. We didn't have the possibility yet to investigate this and try to do it soon. And this work is in process. So I don't know the last question. Last one, it's question from your music as well. Yes, for maybe a question for Clara. There is a question regarding the current share of flax fabric for composites at Linificio. I don't know if it is an easy one to answer.
Quel est le problème, Pierre?
La question, Giorgio, je crois, c'est de savoir quel est le pourcentage du lin qui est produit pour les composites à l'heure actuelle par Linificio par rapport à ce qui est produit pour le textile vestimentaire.
Mais comme il a dit déjà Clara, on a des objectifs, mais aujourd'hui, c'est une très petite quantité.
Okay, so yes, I translate. Yeah, the share for composite at the present time is very low. So Linificio at the present time doesn't really sell very much fabrics for composites, but the idea is to increase this share with the investments which were proposed. So probably with flax, but I'm sure as well with hemp. And I think, I don't know, maybe you can tell that, but we saw on the press that you had people asking if you could provide some of those fabrics for racing cars, for example, or for other applications, if I'm not mistaken.
Oui, Pierre, il faut ajouter que nous, on pense que la méthode qu'il a mis à point, le linificio, avec la mèche et tout ça, va aider beaucoup le développement du secteur des composites parce qu'on pourra faire des composites plus complexes en rapport à d'autres solutions.
Okay, so I try to translate that. So Giorgio from Linificio says that the process which was developed in the frame of the sushi project is particularly interesting. So interesting for Linificio at first because they are now able to offer a whole range of composite reinforcements. And some new complex reinforcement will arrive very soon on the market.
Yeah, sorry, Vincent. Can I add something? So this yes. Complex reinforcements, our engineer told me that has complex shapes, so with folds and different angles. So according to market demands, we can create these complex composites. So with different weights, with different texture, and with different reinforcements. Because of their bidirectional, substrate and characteristics, we can adapt it to the market demands.
Okay, thank you, Clara. And I think our time now is over, and we have to leave now the floor to other work packages. And now Art vanEur is going to present his work.
Yeah, good morning, everybody. I think I have to find my presentation. Is it? Can somebody just help me to pop it up?
I start with my presentation.
Yes, but I had an introductory slide to show who is all coming in this session. But yeah, maybe it's a bit over the additional bit. So yeah, we now do the session on the bio-based composites and functionalities. Thank you. Yeah. So yeah, welcome. My name is Art vanEur from the University of Leuven, KU Leuven. So we'll now do this session on the bio-based composites with their enhanced functionalities. And this is the overview of what we will see. And indeed, Vincent will now just start with an overview of the bio-based composites that were developed in the project. Then I'll come in myself to talk about the durability, and especially in the presence of moisture. And then Gea Spijkerman from Nourion will talk about their developments for accelerators for polyester resins, which are cobalt-free and can also stand the presence of water. And then Mova Louise will finish the talk with a special emphasis on the damping properties of bio-based composites. But indeed, I should give the floor now to Vincent again, yes, to switch presentations. But, yeah.
Thank you, Art, for the introduction, and good morning again to all of you. So I will now talk about the biocomposite applications and the development of okay, let me check. So during this presentation, I will show you the main composites that we have developed and used within the sushi project. Thank you a lot for the sharing. So we used 3 categories of constituents: the fully bio-based reinforcement, the hemp reinforcement, and the polymers developed within the sushi project. So as you can see here, it includes the woven fabrics that were presented just before, the hemp braids, the commingled fabric also, and the different biopolymers, including the aliphatic polyesters for the thermoplastics, and the epoxy from bioagenox and bisguaiacol for the test thermoset systems. On the next, if you can click for the, yes, thank you. The second category is the marketed bio-based polymers, so some polymers already available on the market. So it includes the green epoxy, the epoxy system partially bio-based by Sycomine, a furan resin by Transfuran Chemicals, and the PA11 by Arkema. And on the next, the third category is the marketed flax-based reinforcement by Lineo Ecotechnilene, the flax tape and the flax spray system. It was used for benchmark purposes, proof of concept, and some demonstration activities. So on the next slide, I will show you what we obtained with the 100% sushi composite material, so mixing together the developed bio-based epoxy and the developed M fabrics. So I reminded here the value chain, and on the next slide, you can see the two composites that were developed, one based on hemp fibers and bioethenox. So bioethenox is the first fully bio-based epoxy used in the project from isoeugenol coming from biomass. So we obtained at the end a fully bio-based composite with a TG higher than 150 degrees, mechanical properties similar to GEBA-based epoxy composites with a low ecotoxicity. And the problem that we are facing today is the scale-up of the production, because we need to find a company able to produce in large quantities the bioethenox system. In parallel, on the next part of the slide, you can see the second composite, fully bio-based, 100 sushi materials made with woven hemp and the beeswax-based epoxy. So with this system, we obtained also a fully bio-based composite with a glass transition higher than 100 degrees. We obtained mechanical properties similar or even sometimes overpassing the ones obtained with the GEBA-based epoxy system with a low human toxicity. So as you can see on the top here on this graph, the estrogen activity was measured and compared to what we obtained with bisphenol A, as it was mentioned by Professor Christophe Thomas at the beginning of the session. The bisphenol A is an endocrine disruptor, and you can see this activity here. And you can see that with bis-guaiacol or bis-guaiacol D-epoxy, we have not this activity. So we have a better behavior in terms of human toxicity. The environmental impact was also assessed, and it's lower when compared to the GEBA base, and we have the potential for scale-up. So it's a really nice development within the project. So in parallel, we also used the green epoxy system, so the partially bio-based epoxy commercialized by Sycomine with hemp reinforcement developed within the project. So we obtained very nice results. Most of them were already published, but here I propose you a graph showing the performance at the scale of quasi-unidirectional hemp fabrics in orange color in this graph, and it was compared to two flax reinforcements already commercialized, the quasi-unidirectional Ampitext by Bicomp and the pure unidirectional flax tape by Ecotechnilene. So you can see here that the mechanical properties for the hemp reinforcement are quite competitive compared to this flax reinforcement. And we developed also some aesthetic functionalities with some colored composites, as you can see here. So it can be an additional functionalities for aesthetic aspects, in particular for the design applications. And the last point on this slide concerns the braids. So some braided composites were also manufactured and tested within the project. On the next slide, you can see the developments that we had also. Okay, sorry, we have a problem with the presentation sharing, so it seems to, yeah, it comes back. So on the next slide, we have the results obtained with the hemp fabrics and some furan resin. So furan was also considered as an interesting polymer to obtain fully bio-based epoxy, since it's coming from sugarcane. It's bio-based and it has excellent rigidity and fire retardancy. And we use the furan commercialized by TFC, Transfuran Chemicals. And the main potential problems related to the use of this type of polymer is the moisture release during the curing, the porosities, and the possible acid degradation of fibers and the brittleness of resin. So you can see on the next part of the slide that pre-pregging was done with this resin. It was subcontracted at Basaltex company, and it was performed successfully, you can see on the picture. And then some optimization of the manufacturing process, including the destaging and the moisture release times were performed within the project to obtain a good microstructures with a limited quantity of porosity. And at the end, we obtained a composite stiffness similar to the theoretical predictions, but with a strain and stress at failure lower than expected, certainly due to the brittleness of the resin. So we concluded that this material is, however, suitable for composite application, and in particular for stiffness-based design application. And on the next slide, you can see the last category. So it of composite used during the project. So it's the flax preg system developed by Ecotechnilin, and which were produced by our partners, sushi partners, using autoclave. So it's a fire retardant system which satisfies the self-extinguishing constraints for aeronautics. So a very huge piece of characterization was done at University of Bristol, and you can see that the specific tensile modulus and specific flexural modulus of this material is comparable and sometimes higher than the e-glass composites. So it makes this material a very attractive solution for secondary structural applications. And just a last comment, after the composite scale, we developed also some sandwich structures using the woven hemp skins, as you can see here, with different core materials, bio-based or eco-friendly, like balsa core by Baltec, paper honeycomb by Axor, and recycled PET foam by Armacell. And some more innovative core were also developed within the teams involved in the sushi project, like this one with bamboo rings. So it gives you an overview of the different materials and sandwich structures that we have developed within the project. So I will now stop my presentation and give the microphone to our chairman, Art.
Well, now the speaker, I think.
Yes, the speaker. And thank you, Virginie, for the presentation sharing.
Thank you, Vincent. So can I, from here, again control it, or?
Yeah, normally.
Normally, yes. So the third slide, yeah.
So
I guess people can see on their laptops if it works. Okay, hello. Yeah, so I'm second speaker in this session talking about durability, especially in the presence of moisture. And so yeah, here you see a little bit of an overview of the activities that we will talk about. So first, summary of our work on just hydrothermal aging in the presence of moisture, specifically cycling with moisture. And then there's also a part on the creep performance. So there we bring in mechanical loading combined with moisture and temperature. So quite some nice work was done at the University of Franche-Comté. And yeah, also briefly summarize that. And then also work on fatigue, again, here in France, where we are at the very moment. So let me first talk about the effect of moisture on biofiber or natural fiber-based composites. So usually we can distinguish two effects. There's the immediate effect of the moisture, which will lower your E modulus, and in the literature you sometimes see quite drastic reductions up to 50%. But to be honest, we have done a lot of evaluations in the SUCHY project, and we see more reductions up to, say, 25%. So we will also publish, of course, this work in the near future. And maybe the problem is not as bad as we maybe thought before, but it also clearly depends on the matrix that you use. And so there's a lot of things to find out about that. But in the SUCHY project, we're mainly looking at the cyclic effect of moisture, where you create over time damage, because you get swelling of your fibers, you get, again, shrinking in lower humidity conditions, and all this swelling and shrinking can lead to potential damage. And that's the kind of thing we wanted to evaluate. So here are some strategies to decrease the effect of moisture cycling. And yeah, you see there are quite a few strategies, like using fibers that are maybe less sensitive. But in the SUCHY project, we particularly looked at a few things. That is here actually number 4, where we try to see if we don't dry the fibers. So if we have them already pre-swollen, would that give benefits for the durability, because they don't have to swell all the way from super dry condition. And indeed, that seems to have some benefits, as we will show. Another thing is to work with coatings, either for the composite, but specifically also for the fibers, to put some kind of barrier inside the biocomposite. And yeah, we have also looked at some other treatments, but I'll mainly focus on these 2 aspects that you see over here. So the idea that if you don't dry the fibers, so that you would then create less damage in your composite. Because normally what you have is you go from the fully dry condition during production. When you go to quite high humidities, you will really get swelling of the fiber, and you see all these kind of defects appearing, debondings, fiber splitting. So the idea was, if the fiber is already pre-swollen, it will be more in equilibrium with the real conditions where we use it, because we normally use it between, say, 40 and 85, 90% humidity. So that was the hypothesis that we wanted to test. And then in the first study on polyester resin, this was already published in Composites Part A, we actually preconditioned the fibers at 80% humidity, so quite nicely swollen fibers. And then we did cyclic loading up to high humidity 89 and then low humidity 32. And so corresponding to conditions that you will have in reality. And indeed, we saw here, you see in blue is when you use fully dried fiber, and in red when it was already pre-swollen. Then we have less change in the dimensions of the composite over these moisture cycling events that we undergo. And also you see here for the mechanical properties that in the red is the non-dried fiber, that we maintain much better strength. And this is in transverse direction, so really loading also the interface and the transverse side of the fibers. We keep much better properties over time. You see here the amount of cycles than for the case where we had fully dried the fibers. So this idea really seemed to work. Of course, you can only do this when your resin can stand the moisture in the fiber, and also when during the processing, you don't create steam and porosities and so on. So of course, you have to look for all these boundary conditions. And especially in the case of polyester resin, you need a not water-sensitive polyester, which means a not water-sensitive accelerator. And that is where Gea Spijkerman will soon talk about after my presentation. They developed a non-cobalt, so environmentally friendly accelerator, which is also not sensitive to water, which allows you to do the very thing I'm presenting here. So we did a big second study in Leuven on this whole idea of not drying the fibers and looking at various aspects. So we went not just to polyester, but we also used epoxy. We had fully dry, 50% preconditioned, 80% preconditioned. We benchmarked it with e-glass epoxy, wood, and just the pure resins. And then we did 4 different protocols, so a very extensive study, which is part of the PhD of, well, that's the PhD of Marissa Lou, who is now graduating in March. So congratulations to Marissa for this nice work. So we did also full immersion tests, and then we increased the cyclic behavior that I was just talking about to 20 cycles. And we also did outdoor aging in the full sun and also in the shade to rule out the effect of just the UV. So there's a lot of data, and I'll just highlight a few things because otherwise I need a whole PhD presentation and that would be too much. So here you see some summary of many results. And actually, you see the upper results are for the strength, the lower ones for the modulus, and the left column, say, is polyester, and the right column, epoxy. But in all the cases, we see very similar things. So maybe focus here on the strength of the transfer strength of the flux epoxy. And again, in red is when you fully dry the fibers, and in blue is when you don't dry them, actually precondition them, in this case, at 80% humidity. And you see indeed consistently that idea of not drying the fibers is clearly beneficial. But you also see very interesting difference between the aging protocols. So actually, if you see here SHA and NET, that is the outdoor aging for 10 months. And it appeared that actually the immersion testing was quite predictive in the end for the behavior. So the quite harsh immersion test. And surprisingly, for the cyclic testing, after 20, well, here's the cursor, after 20 cycles, we actually saw an improvement in properties compared to the unaged material. So that was, of course, a very nice extra thing we hadn't expected. So that is, as it concludes over here, that immersion testing seems indeed quite predictive of outdoor behavior. But I have to say this is for uncoated materials. So the water can really get into the fiber and also cause leaching maybe of ingredients in your fiber. And of course, with a good barrier coating, you could hopefully prevent that. And then maybe you would more go back to the cyclic moisture situation. And there it was actually very surprising that we saw, initially we had damage and we saw a decrease, but eventually we saw quite an increase in the properties after cyclic loading. So that is clearly something we need to do further research on. Let me first show you a little bit of we also do damage research, of course, and here you see in this graph the damage that we could measure in micro CT scans and these kind of tools. So the unaged, obviously very low damage, and then after immersion testing, quite some damage, but again, which was corresponding more to what we saw outdoor. And in cyclic loading, clearly less damage than in the other aging protocols. We also looked at the amount of leaching for various materials, and indeed there is a substantial amount of leaching if you don't use coatings as barrier coatings. So that may be part of the explanation of the behavior, both outdoors and immersion testing. But then this big surprise that the cyclic behavior led to an improve in composite properties. So we also just cycled the fibers and then made composites and tested it. And indeed, you see here in blue, well, this is just the modulus results, but both modulus and strength showed an increasing tendency over the amount of cycles. So here actually already after 5 cycles, there was improvement in fiber properties. But of course, in the composite, we have the damage because of the swelling and the shrinking, but it seems the improvement in the fiber properties can later sort of compensate for that. And that is, of course, very interesting. And we need to know more about these mechanisms. And also you see that eventually you take up less water with the fibers. So all very interesting things. And then another study that I would just like to summarize here is the work of another PhD, that is Gilles Kolen. He has looked at putting coatings on the fibers, and eventually you had some nice result with this polyurethane coatings. You see here that we had a significant reduction in the water uptake of the composite, but also if you look carefully here, you can see that after cycling, the retention in properties, so how much remains of the strength is higher than in the case of the untreated material. So there were some significant improvements, and so this is also a promising idea to put some barrier coatings inside your composite on the fibers. Okay, so this was the work in Leuven. Also, very briefly, try to say something about that creep and fatigue work in France, here in Franche-Comté. This is the PhD of Benjamin Sala, and he has done a lot of work to understand the creep behavior in various hydrothermal conditions. And he did creep testing on core materials, skin materials, and entire sandwich structures, which were very important for some of the applications in our project. And he has also tried to do modeling of the creep, which was partially semi-empirical. And here you see some outcome. I just took one graph to show that there was quite a good correspondence between a model in red and experimental results. But to do this, it was necessary to take into account some stiffening of the fiber during creep testing. And that is something we have seen in earlier studies. If you put natural fibers under strain, they can sort of align the fibrils and you can get improvement in strength properties and stiffness. So that had to indeed also be taken into account in this modeling here. And another conclusion that came from this work, that the variability we see on properties of plant fiber composites is actually quite a bit lower when you go to the composite scale than when you do these tests on single fiber scale. So that is, of course, very interesting that if you put many natural fibers together, you have quite acceptable variability in your composite properties, and you get much more results that we also see on glass fiber composites. And then I have one slide about the fatigue results. Well, two slides actually. So also fatigue testing was done in various unusual conditions, you could say. For instance, there was done quite some work on high cycle fatigue, which means up to 100 million cycles, as you see over here. And this was done by using higher frequency. And of course, it was tested, evaluated that this was not a problem with heating of the sample, etc. And you see here very interestingly then the SN curves going up to 100 million cycles. And this led me to ask the question, is there actually a fatigue limit for these materials? Because it seems to still go down, but you see also this is some kind of curvature appearing here. So I guess eventually we'll end up in a fatigue limit, but at quite high number of cycles. And I put one other example graph because there's a lot of information from these studies. I just took some graphs as an example. This is done by changing the temperature. And in black is the standard conditions, in blue is at a very low temperature, -80. And then you see some kind of stiffening and also less steep SN curve profile. And also at high temperature, then you see that actually there's a softening of the material and we end up quite a bit lower. So there is a significant temperature effect clearly on the fatigue behavior, but these are of course quite extreme temperature conditions then that were tested over here. Okay, some conclusions on the cyclic aging and hydrothermal creep and fatigue and so. We have really developed a wealth of data on the durability of plant fiber composites, and there will be quite a few publications coming and have already been produced. We have seen that not drying the natural fibers clearly has durability benefits, and it also saves time and energy during the production, obviously, of the composite. But you can only do this if the resin allows it, and Gea will now soon talk about that, and the way you process it, so not too high peak exotherms, etc. And can you use pressure or not? We had some nice results on fiber coating. And then there was a surprising effect that the plant fibers seem to recover when we do cyclic moisture loading. And that is clearly something we need to better understand for the future.
Okay, thank you. So I'm Morvan Wyss. I would like to show you what kind of properties we can obtain with bio-based composites in terms of damping properties. So, well, this work has been performed in the context of mainly one work package in SSUCHY project, and there have been many contributions from colleagues, including one PhD student, Taishu Liu, and also one postdoc student, Fadel Chatti. So looking at the bibliography, we can clearly see that if we look at the damping capacities of bio-based composites, these materials have very interesting properties. So they have some elastic modulus which are typically lower than synthetic fibers-based composites, but the damping levels are much higher. So there are some promising properties for a wide set of applications where we want to play with vibration or acoustic levels. And so in SSUCHY project, we address several questions which are indicated here. First, we ask what are the physical explanations of these properties? What are the environmental parameters that may affect these properties? We spoke with Art, in particular, of the effect of humidity. We also investigated this in terms of damping effects. And the last question was, how can we go to industrial application by developing specific design methods so that we can take advantage of this damping and damping properties for these industrial applications. So here I mentioned several materials that have been considered in the project, so both from the market and also the materials that were specifically developed in SSUCHY project. So we investigated a lot of different materials. So the first question about the physical reasons explaining the damping properties of this bio-based composites. We propose several contributions to the state of the art. The first one is related to the microanalysis of composite skins using what we call nano-indentation. So this allows to understand at the very micro scale what are the damping properties provided by each component of composite. So you have here, for example, the microstructure of bio-based composite with some fibers and some resins. And we are able now to understand the role played by each of the components at the micro scale to provide the damping, not only in the fibers and the resin, but also at the interface between the two. So this is one of the work that has been possible thanks to the SSUCHY project. Also, we investigated the properties at microscale using some more classical technique like modal analysis using vibrometry measurement to be able to characterize the damping properties at microscale. So these are let's say the smaller scale and the larger one. And we also investigated the properties at intermediate scale to understand the behavior of cores. For example, here some works performed by University of Bristol related to the characterization of the mechanical properties of recycled foams that has been used also in SSUCHY project. Then the next question was, Next question was, what are the environmental parameters that play a major role in the damping properties? So obviously, two very important parameters are the temperature and the frequency of the solicitation to which the material are subjected. So we have performed a lot of investigation on the temperature dependency. And as for many, let's say, viscoelastic materials, we have some properties which are very interesting in terms of damping when we are close to the glass transition of the materials. But for most of the materials that have been investigated in the project, we could observe quite constant damping properties at ambient temperature, which is a good thing for practical applications. And also we investigated the effect of moisture, like Art said before. And if we look at more particularly the effect on damping, we can clearly see an increase of damping capabilities when the humidity is increasing. And so this is, of course, mainly due to the fiber sensitivity to humidity. And we also observed that after drying, if we look at precisely what happens in the microstructure, so these are the pictures which are shown here, we can see that in fact the higher dissipation levels are due to damage in the composite material, which is not very good news, but we have to play with this. So these are some results issued from the project. And then related to the last question, which is the engineering of composite structures using bio-based composites, we have proposed some development on the computational multiscale analysis to estimate the properties, the damping properties of composite structures, starting from the knowledge of the mechanical properties of each component. So basically we have the natural fibers, we have the polymers, and we have the interface. And if we combine all this, we are able to compute some properties at higher scales in terms of dissipation mechanisms. And also when we want to go to more complex structures, in particular plates and shells, we can use some dispersion analysis to perform some homogenizations analysis in order to estimate the behavior of multi-layer panels in terms of stiffness, damping, which are the properties of interest here. And so we could design some multi-layered panels using the sushi materials with very good correlation with between the test and the effective properties which are measured in this case model analysis. So that we could propose some design for the industrial application that will be shown in one of the next talk by the industrial partners of Sushi project. So I think that's all for the damping aspect. So let's see now if we can go back to the previous presentation.
It'd be nice if I can. I hope it now works.
No, not. Yeah, we cannot hear you.
That's difficult to.
So there's a question. Should I reply now, or will we?
Yeah, maybe just go ahead with it. Indeed, the question is if the speaker can refer to it.
Okay, so Inyas asked how we did to measure the damping properties at microscale. So we developed on the specific methodology on the nano-interpretation process in order to be able to estimate the damping using, let's say, something which is quite close to the analysis which is performed on DMA apparatus, but dedicated to the micro scale. So basically, we perform some harmonic tests at micro scale. Well, it would take some time to explain it in detail, but this is the basic idea. And if you have time later, we could discuss about this more precisely. Okay. And also a question by Arnaud Duval. No, we did not investigate the properties in terms of transmission loss. As for the applications that has been investigated in sushi, we were mainly interested in the damping properties in terms of vibration. And so we did not get to the transmission loss analysis, but we have the tools to do it, and we could do it next.
Do you want us to put the telephone on?
No, it's not AFM, it's a nano-annotation apparatus that has been used.
The line by phone?
Yeah, my name is Raymond ten Broeke. I'm also working for Nourion, and I'm responsible for customer service. So we were also joining this project, and our role was to develop accelerators, which could be used to cure in a moisture environment. And in this presentation, we will show you some results about the effect of using cobalt-free accelerators, first cobalt-containing accelerators. So Nourion is it's a chemistry. Hey, sorry, what's happening now? Well, Nourion is worldwide present in a lot of regions. So in Americas, EMEA, and Asia Pacific. And as you can see in this graph, it's more or less divided by region. So most of our revenue, it comes from the Americas. So our content was to develop Nouriact accelerators, and the Nouriact accelerators can perfectly be used to cure biofibers, because biofibers contain more or less a lot of water. So normally in polyester cure, cobalt is being used, and cobalt is used as accelerator to speed up the cure when using methyl-ketone peroxides. Well, also cobalt is being used with natural fibers, but it's very difficult because due to the high water content, well, it's not possible to cure anymore because they are sensitive to hydrolysis. And if you want to have a good cure, you need to dry the fibers first. Drying the fibers costs a lot of energy, and it also has a negative impact on the carbon footprint. And besides that, fibers also take up a lot of water when you store them in a very moistured condition, so they need to be stored in confined conditions. Next slide, please. So Nouriact free cure, it's of cobalt free cure. Our trade name is Nouriact. We have available some accelerators which are not based on cobalt, but they are based on iron, copper, and we have also another one based on iron. In this study, we had a look at the copper-based accelerator, and this is the Nouriact CF12N. So copper is being used there to make sure that you can work with methyl-ketone peroxides to cure unsaturated polyester at room temperature. So it's a very fast and powerful cure. We can cure in conditions up to 6% of water based on the resin. So curing in humid conditions is possible using wet fillers, using natural fibers. Pre-drying is not necessary anymore. And well, in the past, we also showed some results in which you can see that mechanical properties also improved by using Nouriact. So on the right side, you can already see a picture of a chair, and in this chair is being made in a combination of UPR together with biofibers, and is done by infusion. So properties of Nouriact CF12N, it's a copper-based accelerator. They are very high reactive in curing autophthalic resins, but also final ester resins. And lately, we also found out that when curing styrene-free resins, so in this, the monomer styrene is replaced for acrylate types of monomers, you also find a very high reactivity. Besides that, they are not sensitive to water. Negative downside is that pre-acceleration of the resin is not possible. You see a very high gel time drift. And the Nouriact CF12N is a green accelerator. So after the cure, you will see a slightly green color. So what you can see in the table below, it's a comparison between a conventional cure system using our Butanox M50, which is our standard methyl-ketone peroxide, which have a medium reactivity. And we compare this first a cobalt-free cure system, which is Nouriact CF12N. And so the parameters, what you can see in the table, are gel time, time to peak, and the peak exotherm. And this is just determined by putting a thermocouple in the middle of the matrix. And once you mix in the peroxide, the cure starts. And after 40 minutes and 10 minutes, gelation starts. So what you can see in this table is a big difference between the cobalt accelerator and the Nouriact accelerator. The time to peak, you get it much faster. but also the peak exit term is much higher, leading to very fast barcode development. And a very fast barcode development also means that you can demold your product very fast. Next slide, please. Now, what we have in the portfolio, I just mentioned it before. We have NUREACT CF12N, which can be used at room temperature. It's a copper-based one. We have CF30 for higher temperatures, CF40, it's on average, but also CF30, CF31, and CF32. All have their well, I don't know, it's a bit difficult, but all have their specific properties when curing UPR. Next slide, please. The cobalt accelerators, they allow for easy production of biofiber-based composites, and it are premium alternatives to traditional cobalt-based accelerators. And this was actually the part Gea intended to present. So hopefully everybody could hear me and I could explain it a little bit. And well,
thanks, Raymond, for taking over for me. So tomorrow I will do another presentation, and then I think everything is okay. But then we're going to tell a little bit more about the results we got with the hemp fiber fabric we received from you. But yeah, sorry for all the problems I had. And Raymond, many thanks for taking over.
Yeah, you're welcome. And
okay, thank you very much, people from Norion. I guess you can still hear me. So I think we should now swiftly go to the next session because we are 25 minutes behind schedule now. So Fabrizio Scarpa in Bristol will take over talking about the demonstrators. So Fabrizio, are you ready to start your session? I see you. And
yes, I'm ready, Art.
Okay, go for it. Yeah.
Can you all hear me? Thank you very much for the very sweet introduction. Sushi was tasked to deliver also demonstrators out to the materials developed within the project. In the interest of time, I will leave immediately the stage to Craig Miles. Craig is the CEO of Wilson Benesch, and Craig will describe the journey and the type also the products that have been developed within the materials. Craig, the stage is yours. Please go ahead.
Okay, thank you, Fabrizio, for the introduction, and thank you for allowing us to make this presentation. I will begin by presenting the first slide, if you don't mind. Thank you. I'm Craig Mills from Wilson Benesch in Sheffield, England, and we have been fortunate enough to be part of the SUCHY project with regards to producing demonstrators and products for analysis. So when we started this project, this is where we started. And for the purpose of the presentation, I will be using a technical readiness level graphic, which will be appearing at the left-hand side. If you could go to the next slide, please. So this is the technical readiness level, which most people are familiar with. This will appear at the left-hand side of the slide when any major step forward has been made in the progress of the project, so that people can see how we've proceeded through. Next slide, please. So our brief, as I've just hinted at, was to produce component parts and working systems which could subsequently be measured. Wilson Benesch has been in the composites industry for over 30 years. So we had a lot of background in carbon composites, and especially carbon composites in audio applications. We developed a product called the Act 1, for example, which was a loudspeaker which incorporated the first carbon composite product in a loudspeaker system. So this was called the Act 1 after the technology. Next slide, please. So we're a company that not only produces carbon composites, but we manufacture all the metal components that we use in our systems as well. So everything that we manufacture is made in this building. It's designed, developed, researched, everything happens under one roof. Next slide, please. Thank you. We've got a long history of collaborative developments, and this image here is just showing you a torus cone mold, which has been manufactured to shape and form a multi-axial carbon fiber that was developed in a collaborative development. And that particular fiber is actually woven exclusively for Wilson Benesch and incorporates PET rather than an epoxy or a polyester or anything else. We actually melt the plastic to create the matrix to bond the fibers together. So we have a lot of expertise in lots of different kinds of composites, not just pre-pregs and RTM and VRTM, but in thermoforming as well. Next slide, please. All these tools are manufactured in-house, so they're designed, manufactured, and produced on our own CNC machinery. So this kind of capability was quite useful for the SUCHY project, so that we could adjust the molds according to what was required. Next slide, please. Wilson Benesch has always been interested and been driven by economical methods of manufacturing. And we have, since this project, taken a huge step forward in terms of developing new technologies which address the very important requirements of the circular economy. As a forward-looking company, we like to think that this is an important aspect of our business plan, and going forward is going to be a very important part of, I would say, most companies that are forward-looking and trying to address these issues which are essential. Next slide, please. So our starting point was in 2017, and the carbon monocoque that we manufacture was built into a product, and the Act 1 essentially became the first twin, which would be sent to Morvan, Professor Morvan-Louise at the Femto Institute in Besançon. This twin would subsequently be joined by its second twin, which would incorporate the biocomposite, so that the two systems could be compared and contrasted, and clearly some indication as to what the behavior was of the two different systems compared. And Morvan's already touched on these details, so I won't go into it any further, but this was the starting point. And as you can see, we were at technical readiness level 2, which is almost the start of the technological developments. Next slide, please. One of the most important things about Wilson Benesch and its design approach is that we developed our products on what we call a modular design. The majority of loudspeaker systems that exist in the market are in fact monolithic designs. So when they change, the whole product has to radically differ from its predecessor, whereas a modular design is comprised of multiple components which are finished, which are then brought together. So the design of this product is ideal for this kind of research, because we can easily take out one of the components, i.e. the monocoque, and replace it with a different component and have exactly the same system. So nothing changes fundamentally other than the component that we want to analyze. So this was quite a key aspect in the development. It's what we link it to the Porsche 911, because the Porsche is able to develop in this way. Next slide, please. However, the monocoque is a complex system. So in 2019, when we met in Tarbes, we were able to put forward a proposal that we make a flat panel system, so that we could build this into another type of product that we manufacture, which is the Precision series. But this would never be a commercial possibility. It was simply a research tool. And it was agreed that we should go forward with this plan and accelerate our understanding as to what the materials did in a loudspeaker. Next slide, please. So we constructed a vacuum infusion room, and we assembled all the requirements for that processing to take place, and the molded parts were sent on September the 2nd 2019. So the next slide, please. And here you can see the material laid upon the hot plate and the material infused. And on the right of the slide, you can see the comparison of the dry part with the finished part, which we were quite pleased with the finish on that. Next slide, please. And then, of course, the COVID hit, and we had to respond to this. And we made a number of key decisions very early on. We adopted additional premises. We expanded the workflow space to enable people to continue working. And we shifted the whole of the VRTM systems out of the current building into a completely new facility, which enabled us to set up safe working environments for everyone within the company. And on that basis, we were able to continue working throughout all the lockdowns, which was essential. Otherwise, we would never have completed the work that was set out in the project. Next slide, please. So here we are at technical readiness level 3, and this is the first demonstrator that was built into the Precision series, which, as you can see, is a flat panel system, not a monocoque. And this enabled us to get a working system to the Femto Institute for analysis at the earliest possible opportunity. So from March 2019, from there, we were able to assemble this system, and it was shipped to the Femto Institute in August 2020, at the height of the COVID restrictions in the UK. So we did quite well to achieve that under the circumstances, I think. Next slide, please. So, as I alluded to in the when COVID hit, we had to expand the facility to enable us to continue working under the different regimes that COVID imposed. And because of that, we were actually we made a decision to improve on all the aspects of the VRTM so that we could eliminate all the variables that might cause us issues. And so we created a much more highly controlled environment for the system to be worked. We added full extraction systems to this so that we could guarantee that if there were any issues, we could make sure we were working safely. And we completely refurbished all the mold tool systems and the injection systems to enable that to take place. And all the cutting facilities that were required for post-processing were also transferred to the adjacent area in the workplace, so that having been molded, we could go straight to cutting and preparing of the components. Obviously, moving systems around which weigh 250 kilos, like the barrels of resin, also had to be factored in. Next slide, please. So here you can see some of the work that was done by the Femto Institute, and you can also see that this was now looking at the monocoque and predicting exactly how it was going to behave. So we had moved now from TRL3 to TRL4, and as a result of this information that we've derived back from the Femto Institute, we were able to try and aspire to get the amount of fabric into the mold, but it was found that the trying to get as much as what was suggested was quite challenging, because the mold was difficult to close. So we had to start to, at this stage, come up with compromises or different alternative methods of creating the dry pack before it was infused. Next slide, please. At the same time, of course, Bristol were also doing some interesting work, which was very useful in terms of providing data as to how the resin would flow through the mold, because obviously when you're infusing with VRTM, it's impossible to see what's actually happening. So you've no idea where the resin is flowing. And thanks to the work of Dr. Crystal Remila of Bristol, and obviously Professor Fabrizio Scarpa, the software that was used here was previously used by Wilson Benish with Bristol on a previous project, also under the Fast RTM research project. So we were able to actually see the flow of this material as it was introduced into the fiber pack. And as a result of this, we were in a much better position to start infusing the pack with this data. So this accelerated the progress. So next slide. So here is the first PET system, which also has a cork system in it, which was TRL7. Next slide, please. And you can actually see here the two materials that have been used as the core in the monocoque, which has been infused here. Next slide, please. Here are some of the challenges that had to become in post-processing that weren't anticipated, and these challenges still exist, but we are gradually getting on top of them. But TRL8, you can see now that we're almost at the end of the process. Next slide, please. This is a summary just to say that the marketplace for what we have developed is small, but the potential for this development is significant, and we're looking to make a number of new products based on this new technology. And next slide, please. All that remains to be said that the new products that have been developed are market ready. They have now reached TRL9, and we aim to be launching these products in the not too distant future. Next slide, please. It will be good to share all the commercialization opportunities of what we've actually realized under SUCHY, but it's safe to say that the significance of this development is going to be seen on all the new products that are going to be released from Wilson Benesch in the near future. And these are significantly not based on fossil-derived materials, but all on biomaterials. And now we're at TRL9, and I can conclude with my next slide to say thank you to all the partners, and in particular the people who set up this project, Vincent Placé and the team at the Femto, and obviously Fabrizio and his team, and Professor Morvan Luis and his team at the Femto also. Thank you. That's the end.
Thank you very much, Craig, and thanks also for the very interesting journey versus the TRL. I have only a short question from Ignace. Craig, Ignace is asking if you can summarize the advantages of the bio-based materials compared to your standard solution.
Yes, summary would include the fact that the damping properties have been improved significantly. I mean, I think it's possible to say that it's an order of magnitude superior. Stiffness is approaching the same as carbon fiber. The processing parameters that we are now using have reduced the energy consumption by a factor of 50%, which is massive. Processing times have been reduced similarly. So we have made some really significant commercial steps forward with the development, and these are just the beginning. If you're improving the damping properties in a structure that is used in a loudspeaker by this magnitude, it is a massive step forward for the performance of the loudspeaker. Damping is a major aspect of audio design, of course.
Thank you very much, Craig. I'll leave now the stage to Mr. Rosario De Luca, who is the CEO of EADCO and also SILAX GmbH. And Rosario will talk about application of biocomposite for sustainable aviation. Rosario, are you able to share your screen?
Hi, Fabrizio. Yes, I try now. Just let's look.
Absolutely. We can see everything.
Can you see that?
Absolutely.
Okay.
And we can hear you.
Thanks a lot.
Go ahead.
Yeah, thanks a lot, Fabrizio, for the introduction. And yeah, my name is Rosario De Luca. I'm representing here the EADCO GmbH team, which was actually cooperating on SUCHY project on the aviation sector side. Let's say EADCO mostly is a small medium enterprise which is acting
in the aerospace sector. So let's say our main topic was actually to investigate what can be done about the aircraft and airplane to apply with the new upcoming biocomposite materials. And this is why, because let's say we can see that sustainable bio-based composite materials can be really a green alternative for aircraft interiors application, and replacing the old oil-based or other kind of materials, especially for interiors. Let's say even because about the future of mobility, we should try to reduce the carbon dioxide emissions absolutely for the future. And in this direction, we are just not to consider only, let's say, new kind of propulsion systems or all electric propulsion or other kind, let's say, or upcoming new type fuels, but we have also to consider new materials really to get in the direction of the sustainable aviation. Actually, I want just to show a little bit here what we did. The scope of the project was actually to investigate what can be done or where we can apply biocomposite material in an aircraft. Then we find out that maybe mostly, especially to the beginning, we can address the interiors for an aircraft. And this one, because we were investigating stiffness, weight, flight performances, cost as well. Absolutely the recyclable, let's say, side of the story is very important one, and manufacturing process and time consuming. Let's say it was a really hard challenge because, of course, the carbon fiber materials, they are really performing well. And as well, they are low weight structural parts. And then, let's say, we were really challenging a good replacement for such a kind of materials. Then, let's say, what we were investigating were some kind of interiors of the aircraft, and then we down selected the interior sidewall panels that actually are non-structural parts. And at the end, the cockpit dashboard that has a structural purpose on the aircraft. At the end of the day, we decided as well to go for structural, kind of semi-structural, structural parts to test as well the mechanical properties of the materials and physical properties of the materials for structural application. Let's say, from my knowledge, this is the first prototype or demonstrator worldwide about the cockpit dashboard, which has been realized with biocomposite fiber like flax and hemp. And of course, we are still running with the test about the EASA fire resistance tests. They are complained in CS 25.853, and what we considered as a lot of cases actually are compliant with the EASA CS 23561 emergency landing. And let's say about the application, as I said, we were working on flax and hemp. Flax spread and hemp satin, and actually this is how the dashboard looks like. Mostly there is a panel reinforced with an L profile behind, and this one now it will look when will be let's say mounted on an aircraft with all instrumentation related. This one was about the fabrication. Maybe Fabrizio, maybe you can say something more, because it was actually done in Bristol. The manufacturing, it should be nice that if you should add some comments about the slide.
Yes, this is the prototype of hemp epoxy dashboard with a divinyl foam. The dashboard is made out of a sandwich panel. And the digital foam actually is a fossil type of foam, but is one also the few foam materials that are fire tested, also airworthiness tested. So there was a certain element of fossil material that we needed to take into account into these designs and manufacturing. We have used hemp satin layers and put epoxy, which is a type of epoxy that actually is fire tested for airworthiness regulation. We have used a resin infusion technique using unsupported epoxy films, all in autoclave, to provide also very good homogeneity and finish quality, but also relatively low porosity for the laminates. The whole dashboard has been cut from the single panel, and this is the example related to the amp. A similar type of fabrication has also been developed for the epoxy flux tape with the material from Techniland, used as a sort of a benchmark also to verify the manufacturing process.
Thanks a lot, Fabrizio. And stepping forward, after the manufacturing part of the project, of course, there were quite a lot of tests performed, and as well for static vibration and model analysis. They were performed in France under the direction of Mr. Vincent Placé, and as well with the vibration test with Pauline Boutour and Morvan Lucy. And in an article about model analysis, and actually all the results were quite satisfying the requirements. What is here very challenging, of course, are the EASA requirements for the certification, because of course all interiors material there to be self-extinguished material, and they have to be fire resistant. And this is why, because of course we were acting in conformity with CS 25, that actually is for aircraft above 19 seats. And of course, we are still ongoing with the tests that are flammability, heat release rate tests, smoke density, and smoke toxicity. And of course, to qualify the material to be used in an aircraft interiors, we have absolutely to fit with the requirements, and the test has to be successful. Actually, are still ongoing. And then activities are still in progress, are the production of the hemp fabric cockpit dashboard. And of course, we are with the Professor Fabrizio Scarpa and the University of Bristol. They are producing as well a new set of specimen that they will be used for additional tests, especially fire tests. And the next step will be, of course, to get the hemp fabric cockpit dashboard delivered, and to progress with all the required tests to qualify the material, as I said, for interior usage. Thank you very much to all the consortium, and special thanks to Professor Fabrizio Scarpa and Professor Vincent Placé for all the support and all the very good cooperation all this year. Thanks a lot.
Thank you very much, Rosario. Likewise, it is always a pleasure. It's been really a pleasure also really to collaborate with you and your company. In the interest of time, I suggest really to move to the next speaker. The next speaker is Mark Lepela. Is co-founder and director for product engineering of the PSB, the company that has led within Sushi the development of the bio-based scooter. Mark, can you hear me?
I can hear you. Can you hear me?
Oh, yes. So I guess already you can share your nice presentation.
Start up the PowerPoint. Yes, let's share. Is it shared?
Excellent.
Yeah.
The stage is yours.
Okay. Okay, thank you. I'm Mark Lepelaar, co-founder and owner of MPSP Composites in the Netherlands, in Amsterdam. And I'm happy to speak here and talk about the results of our work in the Sushi project. We built a bio-based electric scooter. We already have been producing the scooter since, I think, 2012, approximately like that. But we want to speed up the uptake by the market. So we want to make a stronger, lighter, a cheaper and more sustainable scooter. And yeah, due to the help of the Sushi Consortium, we were able to improve most of these things. We work with a small and dedicated team from Amsterdam, consisting of material scientists, product designers, production engineers, and business developers. And we cooperate a lot with universities and universities of applied science with their students. We have some facilities, or we have already or a lot of facilities. So by now, so we can process different biocomposite techniques, production techniques. So we can do high temperature pressing, we can do cold pressing, RTM, vacuum infusion, and thermoplastic processing. We have some testing facilities as well for mechanical characterization of our products, accelerated aging machinery, and we have products or machines that can help us to bring fibers and fillers to specification. And that's important because besides working with high-end biocomposites, we also try to process bio-based waste streams into not very high-end composite materials, but high-end materials. Yeah. So our mission, we've been active in biocomposites since 1998, and that's our mission to make biocomposites common ground. So yeah, widely accepted material, widely in the market. And we do this under the branding of Nabasco, which is a brand for nature-based composites. Well, everybody who saw this morning's view know that we're talking about, when we talk about biocomposites, we talk about the mix of fibers, resin, and other materials. I will not get into depth here. Well, within this project, we've been cooperating with many universities. We have been doing that since 1998 and continue to do it. And if we want to make the shift from university to our clients, we always have this discussion about this material selection. For this, we use HP diagrams a lot. So here you see the diagram between on the vertical axis, you see the stiffness, and on the horizontal axis, you see the density. And for most of our products, especially for moving products like scooters, we try to optimize the ratio between density and stiffness. And Nabasco you see plotted here. So so it's in between the wood and wood product materials and the composites and metals. So it's less stiff, but a lot lighter than metal, and it's a bit heavier, but also stiffer than wood. And it's yeah, it's a bit lighter than the glass fiber composites. If we look at the specific stiffness for plates, where the volume of the laminate also comes into kicks in, there you can see that on this picture you see on the right all the green composites or the green materials are the biocomposites, and the blue one are either glass fiber composites or aluminium or steel. And you can see here that if it comes to specific plate stiffness, we can beat aluminium and steel, which is an important thing to realize for transport products. If we talk about biocomposites, as I said before, we in our lab we can process lots of different techniques, or we can use lots of different techniques to make biocomposite products, from pressing to vacuum infusion to pre-pregging. And within the SUCHY project, we focused on two materials. So the 5010, which is a natural fiber with partially bio-based resin, where we use vacuum infusion or RTM to make the laminate. And the 110, where we go to 100% bio-based composites, often in combination with the bio-based resin, which is or has use water as a solvent. So there we use the pre-pregging technology. So the N110 is a pre-pregging technique where we want to have the lowest amount of resin possible. Well, as I said, we've been producing biocomposites since 1998. We've been building facades. We did a test with the bridge where we could go to a percentage of bio-based content of 98% in volume and 89% in weight. We work with hot pressing techniques. So this is a BMC technique. We bring this at this moment to the market with for traffic signs and facade panels. And here we use a lot of waste streams. So we use a filler. For the filler, we use calcite from decalcination plants of drinking water. And we use short fibers of maintenance of natural areas. So we use reed, for instance. Then we have a thermoplastic material where we combine thermoplastics, PLA and natural fibers. And the products you see here is a wall paneling and a lamp, which are both 100% bio-based. So as you can see from these pictures, we really try to go to products. The last material we work with, or the latest material we work with is go to 100% biocomposite material, where we work with a furane resin with, for instance, hemp or flax in non-woven and woven form. And here we start to set up the pre-preg production lines and also the product development. So which products to make from these materials. And especially the processing of these materials, we gained the knowledge to do that. We gained from the SUCHY project, for instance, to 100%. So if I come back to the scooter, this is the scooter we studied as a case study within SUCHY, where it's a monocoque structure. We used to make it out of non-woven hemp because at that time there was only biocomposite available besides flax, woven flax. But at that time we thought about reducing costs by using the non-woven material. We made a monocoque structure, which is very stiff and relatively light, and actually it's a really big battery casing in the shape of a scooter, so we can put in a lot of batteries, and it's a very strong and stiff product. I'm happy to say once we had an accident with the scooter. We crashed into a police car, and the police car had 6,000 euros of damage, but our scooter had only one part damaged, and this was a metal part. So we did a live test with this. So it's very stiff structure, and it's an optimum design. However, we wanted to make it lighter because the frame was, although it was a biocomposite monocoque, it still weighed at that time around 30 kilos. Wanted to increase bio-based content because with the non-woven hemp we used, we only had like 25% bio-based content, and if we would use 50% bio-based resin or RTM, then we would have still not a mega content. So we had about 30% of bio-based content at that time. So we wanted to increase it. And what also was important is we used to produce two halves out of with vacuum infusion and glue it together and finish it, which was very time consuming and expensive. So we wanted to lower the costs. So within the sushi project, we developed all kinds of new, or we all did, develop new kinds of materials and also new production technique, because we now use a blow up bladder system where we use pressure to make a good laminate. So we want to produce the monocoque in one hollow part instead of two halves which are glued together. But we did make a prototype. We brought it today. I have a picture of it. But what is important for you to know is that we were able to lower the weight by 56%. So it's a big score. Means that we use a lot less fibers and less resin, and we have a lighter product with the same properties or even better properties. We have a higher bio-based content, so we could increase the bio-based content to 65%. By decreasing the amount of resin and use a partly bio-based resin. And up to now, we did a prototype series, which was still quite labor intensive. But we expect that if we would optimize this and bring it to production, that we could save labor time. So we expect to be able to lower it. However, we have to invest in different molds and work with a higher pressure than we could during prototyping. So here's some pictures. On the left, you see a preform of the natural fiber stitched together to have a scooter body already in 3D fibers. Because of the production technique, we could not work from simple cloth or woven structure, so we had to make a preform which was 3D already. And on the left you see the result of the lightweight body, which was made out of one part. What is important, we were very happy within Sushi that we had a complete value chain on board. I think it's necessary because we want to go to market. So we want to be able to buy bio-based resins in larger volumes. We want to be able to buy the woven fabrics out of hemp. So all these materials have to be brought to the market. And if you want to do research on this, I think you should take the whole value chain in it, and which was done. And we gained knowledge on this material properties, lifespan, and production techniques within Sushi, and developed it for this whole value chain and also for our part. And as I explained, we were able to make a better scooter, which was very nice. And of course, the next step will not only be making more scooters, but also using the knowledge, of course, in other products. Which I presented earlier in this presentation, you can find on our website as well. Okay, thank you.
Thank you very much, Mark, for this nice presentation. Really good to see the Sushi scooter presented already to the world audience and to the also outside the Sushi audience. I will leave the stage now to Arnaud Duval. Arnaud is the Acoustic Innovation and Sales Director of TREV Products, Services Innovation. And Arnaud will provide really the last talk of this session is about the potential continuous hemp fibers for weight reduction and emissions. So Arnaud, I leave the stage to you.
So we'll talk about automotive industry. So I go very fast because we are very light. So we are producing at TREV trims, so soft trims and so-called semi-structural trims. And typically the product we want to replace is a typical load floor, which is a mechanical sandwich, but as we say, semi-structural. So it's within a product family that is, I would say, considered as a commodity. It's not a high value product. It's not a high added value product. which is definitely a difficult situation for us. So what we wanted to reach with the sushi project was to work on the possibilities of 100% bio-based solution, especially regarding the resins and or thermoplastic binder that we could use. Of course, weight reduction and if possible, remain within a good economical situation, knowing that the automotive industry is extremely hard and tough on costs. So today, applications, what we have mainly is definitely based on non-woven. So it's non-woven forms based on short centimeter fibers that are classically carded, napped, and needled. And these products make typical side trims or parcel shelf with a rather low mechanical performance for these short fibers, but a nice, I would say, application in the sense that it is a recyclable product most of the time because we are using classical thermoplastic binder for those applications. But definitely, I cannot call this application composite applications. It's a rather classical trimming without any, I would say, very high mechanical specification. For a load floor, the situation is really different. And what we wanted to solve with the sushi project was to see if we can go out of the classical flax fiber application, which is definitely a nice product that allows to get decimeter fibers, but to our opinion, rather high cost for these technologies. And we wanted to see if hemp could be a good alternative. And you will see, and I will comment that just a slide after, that the main difficulty today is to get long fibers with hemp, classical fiber production and low cost production. And the woven textile form that were produced within the sushi project were a way to look at the potential of the technical fiber hemp in itself without being obliged to tackle the 15 centimeter limitations that we see today when we are trying to do unidirectional tape from hemp. So I will discuss about that at the end of the presentation. So our automotive constraints, it's very special because we are using processes with the less handling as possible, short circuit. We have extremely short cycle time. Here I write 90 seconds. Most of the time it's more 60 seconds that we are actually asking for our processes. So it has to be extremely fast. And most of the time, yeah, we are using thermocompression, thermoforming, depends. And the way we are impregnating our products is definitely a very simple one. It's a spraying. And the spraying is really not the best way to do such a composite. So we are putting, I would say, constraints on one another, short cycle time, I would say unusual impregnation techniques, and simple thermocompression afterwards. So we are not in an easy world. I go very fast on that. It's not. We were very interested about thermoplastic binder. We are not interested in the automotive industry on epoxy resins for the reason that it is a bicomponent product. And when we are stopping a line, it's quite complicated for injection head, typically to be able to stop, reactivate, etc. So it has to go on solvent all the time. So in our industry, we are using polyurethane for bicomponent thermoplastic binding. There are less constraints with the polyurethane, but definitely bicomponent resins are difficult. That's why we concentrate on the sushi project on acrylic resin, where we see interesting new features because there is an increasing content of biocomponent in acrylic resins. There are more technologies, I would say, available on the market now. So things are moving in a good way from that perspective. So reference product is definitely what we call Baypreg. So Baypreg is now completely dominating the market. I don't know if it's 90% of the load floors that are with this technology, but it should be close to that. We were actually at TÜV producing an alternative which was made of 100% polyurethane, but in terms of cost and mechanical properties, we were slightly below this solution. So it's a glass mat, random orientation with fibers of about 15 centimeter long and the polyurethane that is a binder. So we tried within the Sushi project different approaches, but definitely the most competitive one with the highest mechanical properties. In our case, where we are maintaining rather flat surfaces, paper honeycomb is most of the time the most competitive spacer. And we've been playing with unbalanced woven hemp textile and commingled woven hemp, knowing that we focused mainly on the second one. So we have done many various testing and mechanical verification of the properties. So we confirm some things that were proven in the past, that we need definitively to have a specific gluing of the skins onto the honeycomb. So it's a confirmation of things that were known before. We had, and it's explained just afterward, difficulties actually to impregnate our materials. The problem of a woven fabric is that it was rather heavy. We had 350 grams per square meter. And then with a simple spraying technique, there is a problem. The compression in the mold was not solving the impregnation issue. So the weight is slightly too high. And last but not least, we had also some difficulty to maintain an airtightness of the product with the impregnation issues we had. So anyway, we were I would say happy with all the consortium and all the informations that we have been able to share through the Sushi project, and especially to confirm that the hemp fiber has the potential that is extremely close to the flax one, and that there is no big problem behind this. Of course, there is then the constraint of how to get exactly the same long fibers, especially if you're going out of the woven textile. So our conclusion today is that hemp is a good fiber. It's rather, I would say, with a good quality all over the world, in Canada, in China, everywhere, which is always a problem with flax, with good mechanical properties following the Gulf Stream, which is a constraint for our worldwide applications. Of course, a rather more stable cost of the hemp compared to flax, but a woven process is definitely too expensive for our application in the automotive. So we have to come back to unidirectional, I would say, application. So we have early results, and we are working in this direction as well. And our early result with acrylic binder show that the unidirectional M type, even if it is constituted of only 15 centimeter long fibers, aligned fibers, we have a potential of weight reduction of around 15% and a much easier impregnation capability, because we are working with UDs which are weighing 110 grams per square meter instead of 350 in our case. So it is solving partially the impregnation issue, even if we are keeping our spraying technique, which is definitely a constraint with the automotive cost. So thank you very much for your attention, and that's what I wanted to share with you now.
Thank you very much, Arno, for your presentation, and thanks also for sharing your very interesting comments about the value of AMP, also within really the business of your company, and also the wider context of use AMP in several industries. For the interest of time, first of all, I thank all the speakers because you have given a really an excellent evidence of the technology readiness levels that have been acquired and reached within SUCHY. And I'll give the stage to Professor Karel Veracker from the KU Leuven. And Karel will lead the session about the environmental sustainability of the bio-based composites. So Karel, can you?
Yeah, thank you very much, Fabrizio. You can hear me, yeah?
Yes, I can hear you, I can see you.
Yeah, it's a short session. It's only one presentation. It's the presentation about the sustainability of the materials that we have been developing in the project. And if everything goes well, you can see the presentation now. Yeah. Okay, so the question that we were dealing with is what are actually the potential environmental impacts of the solutions we developed in the projects. And if we talk about environmental impacts, we normally look in a systematic way based on established life cycle assessments. We look to carbon footprint, water footprint, ecosystem biodiversity, and all kinds of environmental impacts. Although that this presentation comes at the end of this morning, I can assure you that this was not just an add-on on the project, but we have been working very interactively with all the researchers, and we could also give some guidance for choices made during the project, and that is how it should be done, so that you look at environmental impact of choices of solvents, of sources, and so on, so that we can develop materials that are indeed as environmental beneficial as possible. Okay, we did that, or what I will present is only the results we have for the 4 demonstrators shown in the previous session, but of course we have developed this life cycle assessment for the full life cycle, starting from the cultivation of the hemp until the composite material itself, the curing, and looking at its functionality. I will focus this presentation, since it's very short, only on the CO2 footprint of these materials, and mainly looking at the production, although we also included the use phase of the demonstrators, and also some scenarios, some very conservative scenarios for the end of life of these products. And something that you have to keep in mind is that with these LCAs, we look at, for example, CO2 footprint, but what we do not cover is the advantage, the benefits we have of the renewability as a resource, also issues with resource dependency, which are very actual today with the COVID crisis. And that, we based our assessment on what is developed within the project, but of course, it is not a very fair comparison with very established technologies. And so you can foresee that there will be further technology evolution. So to come to the first demonstrator, the floor panel, which was actually the last presentation in the previous session, what we did see is, if we compare here at the right side with a benchmark scenario, the polyurethane with fiberglass reinforcements, that we can achieve with the SUCHY solution that we can achieve about around 50% reduction for two different systems that we considered, the flex one and the hemp one of the SSUCHY product, the SSUCHY project itself. So this is very encouraging, I would say. This is only concerning the production. If you also include the use phase, then actually the gain you have is because of the reduction in weight. But the reduction in weight is still quite limited if you consider the entire weight of a car, which is obvious, but still we can reduce depending on the mass reduction that really can be achieved up to 0.75% greenhouse gas or global warming potential. That's taking into account still combustion engines. For the end of life scenarios, that has to be discussed considering all environmental impact indicators. That's important there. But if you look at the full life cycle, including this use phase, it seems to be quite quite modest reduction in global warming potential. But this is still already quite impressive, I have to say. And if we move to electrical vehicles with greener and greener electricity grids, let's say, then of course the production phase where we can reduce 50% of this global warming potential becomes much more important. Then the second demonstrator was the monocoque of the scooter. Also there, we looked at the entire scooter frame. We compared with the steel frame of today, the benchmark scenario here. Also there, we see today, if we use the solution that is available today, epoxy-based biomonocoque, we have a reduction of 37% in greenhouse gas emissions, leading to global warming potential. But we could go, if we look to the future, and we can also use, for example, the bisglycol-based resin, we could go to a 60% reduction. We have included all kinds of scenarios also for the use phase. We considered an electric engine, which also has an impact still, since you take, or we have taken the European electricity mix into account, which is not fully green, of course. It also has some impact on global warming. And we also had some very conservative end-of-life options. But if we compare then, we also see that we, over the full life cycle of these products, we can achieve up to 11% reduction. For the loudspeakers, there we only have to look at the production phase. We could not include the benefit of the damping properties, for example. But also there we see that for these materials, we can indeed go to even higher reductions in global warming potential. And finally, for the aircraft dashboards, even for the production, we even have further possibility to reduce global warming potential. For such demonstrators, it's 82% in case of epoxy flex and 76% in case of epoxy hemp. If we develop further and we use, for example, the bisglycol resin in the future, we can reduce even further. So to conclude, actually, this short presentation, I think that we can say that resulting from the very extensive analysis that we did, and I only showed the final results actually here, we can conclude that there is indeed a high potential to reduce the CO2 footprint which we hoped for, of course, at the start of this project, and which is not evident, I have to say, for bio-based materials. But there is indeed, for the solutions developed in this project, a high potential to reduce up to 2 times the CO2 footprint in the production phase. So especially during the production phase, there is a reduction. The full life cycle, there we also have impact of the energy consumption in mobility that lowers a bit, and we also have these end of life scenarios that lowers a bit the entire benefits that we had with the production, but it's still beneficial in terms of CO2 emissions. We also look to other environmental benefits, and we all know that if you go to bio-based materials, you also have to carefully look at the land use you need for it, water depletion, although I can say that this is not larger than in the benchmark solutions if we use the hemp in eutrophication. And finally, again, that are the environmental impacts during production, during use and end of life. But there are other benefits to the environment, such as the depletion of metals and minerals, which is now replaced by renewable material if it is well considered, of course. Okay, these are the main conclusions, and with that, I give the word back to Vincent, I guess. Yeah, there is Vincent.
So thank you a lot, Karel, for this really interesting presentation and for giving all the details regarding the environmental footprint. It's really an important objective in the SUCHY project, not only to have a bio-based material, but also to be able to assess this impact. So it's really interesting to have this talk as a conclusion of all the scientific developments. So thanks a lot, Karel, for this. I don't see any comment or question in the chat, but I encourage all the participants to write directly to Karel if you have any question. And before closing the meeting, we have the great pleasure to welcome our project officer at CBE, Anna Ruiz, for the closure talk of this final event of the SUCHY project. So Anna, I invite you to take the floor and give you the microphone for your presentation.
Yes.
Anna, I don't know if you can
yes.
hear
Can you
us.
hear me?
Yeah, perfect.
Okay. So let me share my screen first of all. So first of all, well, thank you really very much for inviting me to say some few words at the end of this important conference of the SUCHY project. It's really a pleasure for me to stay today with you. I know that we are very late in the agenda and in the timing, so I will try to be fast. My message are not long, so only a few words, because I want to highlight what important is this project for BBI and for CDE. This project was selected for funding in the year 2017 is when the project started, and after 4.5 years after is a clear example of a success story of a project and how can contribute to the objectives of the BBI and in general to the circular bio-based economy. First of all, I want to really thank the coordinator for the excellent work, cooperation, and communication we have all the time with you. And also thank you so much for all the hard work to all the consortium, which has ended in a very good presentation of results, and the delivering of achievements is really clear. So congratulations for all the work. And only I want to highlight, you have discussed a lot about what has been achieved, the impact on of your work, and how the work that you have done has delivered an improvement on composites with advanced functionalities, and all the work validating these activities in industrial demonstrators, which I really think is great. Only to highlight that your work contributes to several of the PDI and currently CDE-EU objectives, in particular helping to replace bio-based chemicals in materials, and to replace all the fossil-based counterparts by these bio-based materials, reduction of CO2, and also is a great success to support the development of new companies, new source of sustainable growth. I'm fully convinced about that. And my end words to say that we really look forward what is going to happen now that the project has ended. We really encourage to apply and to continue doing, apply what you have already achieved, no? And why not to present a new proposal and the new opportunities that they will be open with the new joint undertaking, and maybe to move the RIA to a demo, and ultimately to go to the commercial implementation of all what you are doing. So please count on us. CDE-EU is at your disposal, and really thank you for your work, and good luck for the future. Thank you very much.
Thank you, Anna, for the talk, and sorry, I have an echo, for the talk and for the kind words, and thanks a lot also for all the support provided all along the project. Thank you to BBIGU and CBGU also for supporting us from the beginning of this story, for having trusted in our ideas, and yes, for giving us the opportunity to develop these activities and to reach this point. So we are really grateful to BBIGU for this. And apologize for the delay. We are really late, so sorry, we faced some technical problems. It's not so easy to organize everything in hybrid mode. So I would like to apologize for this. And I would like also to thank again all the speakers of this day and all the attendees. In case you have additional questions, you have now our contact, so please feel free to address your questions or to contact the consortium members to have more details or to further the discussion initiated during this event. So again, I would like to thank all of you for attending this event and wish you all the best for the future. Have a nice day, and hope we can see you soon. Bye.